Okay, let's move on to section 2.3, the Faraday's law. So, starting from this section, we'll begin with discussion about Maxwell equations, which includes the Faraday's law, the first one. The second one is Ampere's Kirchhoff law, and the third and fourth one are Gauss's laws of electrical field and magnetic field. So here's the Faraday's law, which was concluded by Faraday, who had done many experiments about interaction of electric circuit and observation of magnetic fields. So in 1831, one interesting fact that found and reported by Faraday is he found that time-varying magnetic field can give rise to electrical field, and therefore it's referred to as the Faraday's law. So the experiments can be illustrated as the figure shown. So as you can see, you have a permanent magnet, a coil which has electrical wire wrapped around, and as the magnet moving in and out of the coil, we observe that there are voltage generated due to the movement of the magnet. So one important thing to notice from this experiment is that the voltage, the electrical potential, the electromotive force is not produced by the presence of the magnetic field, not because of the presence of the magnetic field. It is generated by the change, the time variation of the magnetic field. So as you can imagine, as the magnet moving out, and we know that how the magnetic field lines can be drawn around the magnet. Well, so there are closed loops wrapped around the magnet, and as the magnet moving in and out of the coil, the amount of magnetic flux intercepted by the coil changes as the time varies, as the magnet moves. So if the magnet is placed in a stationary position, there will be no electrical potential associated with it. However, as the magnet moves back and forth, the voltage can be produced. And as you can see from this plot, from this figure, the polarity of the electrical potential is different when the magnet is moving in and out of the coil. So the polarity of the electrical potential, that is the voltage accumulated in these wire loops, is associated with the decrease or the increase of magnetic flux. So we know that the change of time-varying magnetic field is associated with EMF, with the electrical potential, and this voltage is referred to as electromotive force, which is abbreviated as EMF. Okay, so to sum up, time-varying magnetic field produce electromotive force. Okay, and turns out in Mandarin you can explain that 时变电场产生电流那这个电流就代表 你的线圈里头是有电位差，是有电压降的哈，有感应电动式。Okay. So the variation of magnetic flux can result from so in this slide we will discuss a few causes, a few sources for time varying magnetic flux. 时变的磁通量 time varying magnetic flux can be due to the time variation of magnetic flux enclosed by a fixed loop. Okay, so it's kind of a change the magnetic flux density B as the time change. The second cause can be a moving loop in a static magnetic field. So if the position of the loop changes as time progresses, even though that the background magnetic flux is stationary, we will experience different amount of magnetic flux. And the third cause can be a combination of the two. 所以第一种的状况是什么？你的线圈固定不动，但是你的磁场随时间改变，就像前一页所看到的动画一样。那第二种状况就反过来，也就是说你的背景的磁场分布没有变化，不过这边有一个前提，也就是说你的背景的磁场分布要不均匀，不是全体一致，不是全体均匀。这样的话，你的线圈可以透过改变大小，或者是改变它的方向。因为你改变方向的时候，它所拦截到的有效磁通量就会不一样所以它也会造成磁通量的时间变化所以重点是磁通量的时间变化，而这个磁通量的时间变化可以来自于背景的磁场改变，或者是用来接收磁场的这一个线圈，它随着时间改变位置，或者是改变大小改变位置或改变大小。那这两种的来源各自或者是结合起来，都可以让我们去感受到这一个时变磁场所造成的感应电动势时变磁场所造成的 EMF。 Alright, so to express the Faraday's law, to express the to sum up the Faraday's observation in terms of mathematic form can be written as equation 2.13. So even though that I didn't ask you to memorize this equation, but I will recommend to look at the equations as many times as possible, and eventually you will well, you don't have to memorize it, but once you understand the intrinsic meaning of this equation, I bet you can memorize this equation by heart. All right. So the equation says the closed loop integral of the electrical field of a certain area, of a certain path. A certain path. So this is the electrical field intensity. Electrical field intensity. What is the physical interpretation of the line integral? The line integral of electrical field intensity is what? Is V, the voltage, or the EMF, electromotive force, or electric potential. Equals to what? Equals to the negative of time varying rate of magnetic flux accumulated or intercepted by the surface area enclosed by this path. So you need to notice that the ds is associated with C, the contour. The contour. So here you have a closed loop C, or a closed loop, closed contour, and the magnetic flux passing through this contour, or the surface area enclosed by the contour, is summed up as what? As phi, magnetic flux. And if the magnetic flux can be changes with as the time varies, then you will end up with magnetic electromotive force. You will end up with electrical potential. So in Mandarin, the Faraday law says 在封闭回路中的感应电动势等于其磁通量时变率的负值。So the electroparaday law says that the electromotive force around a closed path equals to the negative of the time rate of change of the magnetic flux enclosed by the path. So to illustrate this idea, you can see that in the figure down below, you have a contour. And the surface S enclosed by the contour doesn't have to be a planar surface. It can be a curvature surface area as illustrated in the plot. All right, so it doesn't matter if this is a planar surface or a curvature area. All the magnetic flux passing through the surface is the same in this equation. And this property, these characteristics also suggest one important fact is that the magnetic flux or the magnetic fields always end up in a closed loop. To ensure that this assumption is valid, 也就是我们刚刚看到的也就是说你那个 contour C 所围绕的面可以是比较小的平面，或者是比较大的，像这个图中所看到的一个半蛋壳的那个曲面。不管你是用平面去计算，或者用曲面去计算，算出来的那个磁通量是一样的。为什么？因为这些磁力线都必须要绕成圆，所以只要它有穿过这个 contour 的内部，它就会穿过所有这个以 contour 为边界的面。所以我这边要强调的就是说，磁力线它会是成一个 loop， 成一个圆圈的，它是没头没尾的，不像电力线是有头有尾的，电力线是有头有尾的，但磁力线不是不是不一定，不是所以你这个面积分才会，只要边界 C contour 是相同的，那结果都是相同的。Okay. All right. So there are certain procedures and observation of interest pertinent to the application of equation 2.13, which is the first Maxwell equation. So equation 13 itself is the first Maxwell equation, which is referred to as the Faraday's law. So here are some rules of thumb about this equation. The first one is the magnetic flux on the right side of the equation is to be evaluated in accordance with the right-hand square rule. Okay, this is the right-hand square rule, which is abbreviated RHS, is followed in most engineering disciplines, which is also true for the study of electromagnetics. 所以记得用右手定则哈，用右旋的方式来去进行这一个面积分 ，OK 哈，所以说右手的方式告诉你，右手的方式就告诉你什么？告诉你那个面的方向是哪一个方向 ，alright 哈 ，so yeah, in previous lectures I already told you for a closed surface, the normal direction of the surface is always pointing out of the region enclosed by this closed surface. How about for open surfaces? That is a surface with edges, right? And it depends. If you define the direction of the edge, if the direction of the surface edge is defined like this, then the direction of the surface is determined. If there is no definition of, if there is no indication of the direction of the edge of the contour, then you can say, it has two surface normal, one is pointing to the right, the other is pointing to the left. However, if I told you the direction of the contour is this way, then using the right-hand square rule, you can say that, the surface enclosed by this contour is pointing to the right. Well, at least this is the positive direction. The positive direction. If the flux is passing through this surface from left to right, then the sum of the flux is positive, and vice versa. Okay? If the flux is going from right to left, then the sum of the total sum of the flux is negative. All right. So be careful about the right-hand square, which means that if you see a surface with edges, you need to check if it has an indication about the direction of the contour. All right? And as we have seen in the previous slides, that as long as the contour is defined, then the so-called surface enclosed by the contour, any surface enclosed by the contour can be used for the calculation of Faraday law. So here is an example to illustrate this fact. That is a slanted surface that has intersection on x, y, and z axis. And the edge intersected by this slanted surface, and the three coordinates can be seen as line PQ, line QR, and line RP. All right, and the edge of the contour is defined as C. So what is the direction of the contour? Or what is the direction of the surface enclosed formed by the three edges? So as you can see here, using the right-hand square rule, the surface normal is pointing top right, from your perspective, right? Okay. And in the figure to the left, you see the surface is determined as a planar surface enclosed by the three edges. Nevertheless, the figure to the right shows an alternative interpretation of the surface enclosed by the same contour, which is formed by planar surface on xy plane, on yz plane, on xz plane. And even though that the surface area is assembled from 3 planar surfaces, it's still a valid surface enclosed by the same contour, even though that they look different. It looks different from the one to the left. The calculation result of the surface to the right is the same as the one to the left. So the magnetic flux through all such surfaces shall be the same in order for the electromotive force around the contour C to be a unique value. So in a defined contour, in a defined closed loop, the electromotive force is a unique value. So no matter, as long as the surface is determined by the edge of determined by the contour, the surface integral result of magnetic flux is the same. Are the same for the same contour, for the same closed path. All right, and the next thing. The third one, the closed path C on the left side needs not to represent a physical wire loop. Doesn't have to be a physical wire loop. It can be an imaginary loop in the space. So it means that the time-varying magnetic flux induces an electrical field in this region, and the collection of the magnetic flux shall provide the electromotive force around this closed path. All right. So even though that you don't have a physical wire in place in this region, but the potential. 我说这是一种势嘛，就像我们在做电场的积分，给你的是电压，给你的是电压，而这个电压呢，你必须要把一个一个带电粒子，一个电荷带到这一个场的环境中里头，你才会感受到这个场的作用，也就是电场作用力，但你没有把那个带电粒子带进来，并不代表这个环境中没有那个电场，没有那个电位能，没有那个电压降，它一直都在。而同样的道理，同样的状况也发生在磁场的作用上面，也就是说，你只要能够在这一个有磁场、有实变磁场的环境中，给它一个封闭的电线回路，封闭的电线的话，那么它会产生感应电流，它会感受到这边的 EMF 产生这个感应电流。所以没有那个线圈，不代表那个 heat 那个势不在那里它就在那里。那就看你有没有把线圈带进来带进来的话，你就可以观察到它所造成的影响。Okay. So if a wire is placed in the position occupied by the closed loop, the EMF will produce a current in the loop simply because the charge in the wire are constrained to move along the wire. Because the time-varying magnetic field produces an electrical potential in the space. So but you need a closed loop so that the electrons or electrical charge reside within the wire can be moved according to the direction, according to the electric potential. So to sum up, if you have a closed loop in a time-varying magnetic field, the electron will be moved by the electromotive force to form electric currents. So this equation can be simplified or this equation can be memorized simply in terms of 磁生电。不过这句话有点太简单了啦，应该是说时变磁场生电场。OK 时变磁场生电场简单讲就是磁生电嘛所以试着你再看一下，这边是对时间的微分这边是对时间的微分，所以时变磁场生电场而这个电呢，当然了，这边的物理意义是电压，而它代表的是一个区域中电场的计算，就是把这个电场沿着一个线圈、一个 loop 做线积分所以它代表的是什么？它代表的是空间中的电场分布不均匀。所以整套的那个 Maxwell equation， 它的等号左边都是电场跟磁场的空间分布，等号的右边是电场跟磁场的来源，还有电场跟磁场的时间变化。这个没关系，我们几个式子介绍完之后，你大概会有这方面的感受。然后第二章我们讲的是积分形式的，你在这个关系在第三章微分形式的 Maxwell equation 可以显现得更清楚也就是等号左边是电场跟磁场的空间分布的不均匀，而这个空间分布的不均匀是来自于电场跟磁场的基本来源，也就是电荷跟电流的存在，还有电场跟磁场的时间变化所以等号的左边跟右边其实物理意义是不太一样的右边是 source， 左边是结果所以右边是告诉你时变电场、时变磁场、电压、电流是电场跟磁场的来源，而左边告诉你有了这些电场跟磁场的来源之后，它就会造成空间中的电场跟磁场的分布不均匀所以因果关系来要搞清楚 ，alright？ Okay, and one interesting thing about Faraday's law is the minus sign. So it's kind of difficult to It's a little difficult for you to memorize the equation. It says that the closed limiting growth of the electrical field is the negative of the time variable rate of magnetic flux enclosed by this closed loop. The negative itself says a lot of things about the equation. So the negative itself is referred to as the Lenz law, 冷次定律 the Lenz law. The minus sign on the right-hand side, together with the right-hand square rule, ensure that the Lenz law is always satisfied. Lenz law states that the sense of the induced EMF, such that any currents produced by the electrical potential, is the purpose of the induced electrical potential is to what? Is to act against the change. Act against the change. 所以我们只要进到那个50年前的中国的话那个冷次定律就是妥妥的反动分子OK 所以冷次定律是什么？对抗改变，维持现状，不要改变。所以我们可以简单想就是这样的Lenz law oppose the change in the magnetic flux. So it's important to note that the induced EMF acts opposed the change in the flux and not the flux itself. Okay, so to sum up, it says the induced the equation, the Faraday's law says for the Faraday laws to take effect, which means that for you to observe electric potential produced in this region. The first thing is the magnetic flux. The amount of magnetic flux changes as the time varies. The flux can be a greater number or a smaller number. Okay, it becomes larger and larger, or becomes smaller and smaller. And as a result, it produces the electromotive force, the electric potential. And the produced electrical potential is acting against the change. Because the electrical potential, which shown as a current, and you know that according to Ampere's law, currents produce magnetic field. So we shall compare the polarity of the magnetic field changes, magnetic flux changes, and the polarity of the magnetic flux produced by the induced current. And it says that the induced the magnetic flux produced by the induced current is to act against the change of the original magnetic flux changes. All right, and yeah, we probably can see another example very quick later. And the fifth thing we need to notice that, which is a common practice in the circuit design, you can see that the the electromotive force, EMF, can be enlarged using coils, using spirals, using multiple loops of wire, so that the electromotive force can be a greater number. Using wire loops. Okay. Why do we need loops to enlarge the amount of electric potential? Well, if you want to have a large electric potential, you need to. There are two ways to do that. One is enlarge the amount of change. That is the amount of magnetic flux change can be made greater, which means that you need larger and big devices to do that. And if you do this, then the induced EMF is enlarged, and the currents induced by this EMF gets larger as well. And since most of you are 电机科的同学上来的嘛，所以你们在做以前的基础的电工实验，其实就要小心的一件事是什么？人不是给高电压电死的，人是怎么被电死的？是被大电流电死的。所以大电流这件事情不安全了So to limit the amount of currents, so instead of increasing the amount of current, we use an alternative approach, that is to employ the coil wire configuration to increase the amount of EMF without directly increase the amount of current. Okay, so that's one of the reasons why we see coil devices in the circuits, which uses this principle to enlarge the amount of inductance. As a result, you see a larger inductor because the coil configuration can be approximated as an inductor device, and it simply enlarge the amount of EMF by increasing the number of turns, so that the EMF intercept or the change of magnetic flux can be multiplied by the number of N turns, by the number of the coil. All right? So this is a very simple mechanism that we employ to improve the efficiency of electric circuit designs. All right? And so let's check with some examples. So example 2.3, a time variant magnetic field is given by B equals to B sub 0 times cosine omega t. So the expression itself says this is a time variant field. And the equation, the associated equation is cosine omega t. So what cosine omega t says? Cosine omega t is a sinusoidal function. So t means it changes as the time progresses. And omega is what? Omega is angular frequency, 叫频率吧, angular frequency, 叫频率, which is what? Omega equals to what? 2 pi f. That is the radian times over a period times the frequency. So that is the amount of angular change within fixed amount of time. Okay, so if we have, for example, our electrical power source is referred to as 60 hertz. The frequency of our power system is 60 hertz, which means the phase of the power currents will change 2 pi times 6 in 1 second. So if F equals to 60, yeah, then the angular frequency of the power signal is 120 pi. 120 pi. So, of course, this is time variant signal. And if you see the magnetic flux density is pointing to which direction? The positive y direction. And in this illustration, I don't know about you, when I check a paper or the textbook, the first thing that I would notice is figure. So anything that cannot be fully explained or expressed in terms of text shall be accompanied with a figure. So figure is important for you to understand the true implication of the author. Okay, so if the author thinks it's necessary to put a figure on his paper or on his textbook, well, which means this means you need to pay attention about the figure. All right? So in this figure, of course, you illustrate the scenario of this example. And when you look at the figure, first thing to check is the coordinate system for this example. Check the coordinate system. Which is the x direction, which is the y direction, and which is the z direction. X, y, z. Use your right hand to check if the plot is drawn correctly. Well, in my academic career, I've reviewed more than hundreds of papers, and it does happen. It did happen. Some papers drawn the coordinate system incorrectly, so that, well, good. Then this paper is kind of a garbage. Well, yeah. If the author cannot draw the draw the coordinate system correctly, right? So check out the coordinate system. So y is pointing into the screen. Yeah, so as you can see here, the cross signs here on the screen are magnetic flux pointing into the screen, right? And what is the direction of the loop area? So here you see a contour placing on the xz plane. And the area of this loop is the product of its length and its width, which is A times B. And what is the direction of this contour? Positive y or negative y? Positive y, because the contour rotates clockwise. So it's pointing into the screen, which is the same as the magnetic flux. All right. So the area or a small region in this loop is ds, which has the direction of positive ay, and the area size can be expressed as dx times dz, according to this right-hand square rule. And the total magnetic flux enclosed by this contour can be found using this surface integral. So here you have the description of the surface, which is dx, dy, ay. And you have the direct description of the magnetic flux, which is B sub 0 cosine omega t ay. So fortunately, because the two vectors are both pointing to the y direction, so their scalar product is non-zero. On the other hand, if the magnetic flux density is pointing to the x direction or z direction, then you don't have to carry out the calculation, the integral. You don't have to carry the integral because you have 0 for your integram. And in this case, the integram, well, fortunately, because the surface integral is a double line integral in the x direction and z direction, unfortunately, because everything in the integram are not related to x or z, it's not related to x nor z, so everything in the integram can be moved out of the integration as b sub 0 cosine omega t. And the simple integration of this surface area becomes A times B. So you end up with the expression for your magnetic flux phi as A B sub 0 cosine omega t. Okay, but this is not your end product. Your end product should be found. Your end product, that is the electromotive force, which is the closed loop integral of electrical field, is the negative of the time rate of phi. That is, you need to take a time differentiation and then take the negative value. So the time differentiation of cosine omega t is what? It's minus sine omega t. And the minus sign is cancelled by the minus sign in the front. So you end up with an EMF, the electromagnetic force, as A B sub 0 sine omega t. Now, that is the electromotive force or electric potential produced by the change of background magnetic field in this loop area, in this surface area. All right? And if you draw the two, that is the magnetic flux and the electric potential produced according to it, it's a simple differentiation operation, as you can see here. So what is the purpose of differentiation in the time domain? The differentiation in the time domain is to indicate the change, the rate of change, the rate of change. So it does not relevant to the amount of the original field. It's emphasize the rate of change in your original physical parameter. So as you can see here, in the zero crossing area, you have the greatest rate of change. So here is one that goes from a positive value to a negative value, and because of the minus sign, according to the Lenz's law, it gives you the maximum in the EMF in the time domain. And on the other hand, at this zero crossing, which is goes from negative to positive, it produces the largest EMF, the largest negative EMF, because of the Lenz's law. And on the other hand, at the peak of your magnetic flux, the amount of change is relatively small in this region. So you end up as zero crossing on the electromotive force. Okay, so this example shows you that the electromotive force is associated to the time rate, time variant rate in terms of the magnetic flux. Alright, the polarity in this figure is exemplify the polarity of the current give rise to a magnetic field directly into the paper inside of the loop, and hence acts to oppose the decrease of the magnetic flux enclosed by the loop. So let me explain this a little bit. So as this plot shows, the magnetic flux is decreasing now, which means there are less and less crosses on the plot， 叉叉变少了，所以在这一个时段里头，叉叉变少了，那看一下你的 EMF， 在这个时段你的 EMF 是变大了，那意思是什么？沿着这一个顺时钟绕的电流量应该要变大，为什么？因为电压变强了嘛，电压变强了，所以它驱动的电流值变大，而它驱动的电流值变大，来右手过来，电流变大变多，那表示这一个电流所产生的磁场，这个电流所产生的磁场在哪个方向？叉叉方向，也就是我图上画的红叉叉。也就是说你的感应电流是要去产生这些红叉叉的，所以你可以简单想，这些红叉叉的目的是什么？是要补那些原先消失的黑叉叉嘛，对不对？所以原来的状况是黑叉叉在这个时段是黑叉叉越来越少，所以你产生感应电流去补那些红叉，用感应电流产生这些红叉叉去补那些黑叉叉，所以这个就是冷次定律对抗变动也就是说你的感应电流、感应电场、感应磁场其实都是要对抗变动的所以我们可以简单讲，冷次定律是要维持现状、对抗变动。但是假如你在50年前的中国党就会说什么？对抗变动是徒劳无功的OK 我们继续变动即便你对抗但是还是会变动。等到变到更小的时候呢，你的那个到超过这个点的时候你就从补叉叉变成补点点的OK 就会再反过来Alright. And here's another example, but I think our time is limited, so I would like to stop here.